The subject is communication, and what a challenge it presents. A simple view of communication is that it involves transfer of meaning between people. Communication is not possible without language of some sort, and that language can be the source of the biggest challenge to effective transfer of meaning. Amongst other reasons, ineffective communication between two people might be because either one doesn't understand at all the words or symbols that the other uses, or, and sometimes this is worse, to one person, the words and the symbols that are used mean something different to one of those people than they do to the other person. Now, language that's specific to a particular field of endeavour is what we call the jargon of that topic. And just as there's a jargon of football or of criminal law or of architecture, so there's a jargon of chemistry. And a subset of chemistry jargon is particular to the topic of dynamic chemical equilibrium. And the topic of chemical equilibrium is full of its own particular jargon. Even the label that we use, dynamic chemical equilibrium, the term equilibrium in chemistry means something entirely different from its meaning in relation to human emotions or physical systems in a state of balance. The jargon particular to this topic includes terms like reactants and products, not quite as simple as you might have thought, net reaction rate, perturbation of system at equilibrium, equilibrium shift to the left or to the right, spontaneous. Now, it's probably true that between any two people, there's never perfect commonality of understanding language. But if there's not a reasonable degree of shared understanding of what terms mean, then miscommunication is probable. So, my purpose is to clarify the precise meanings of the jargon terms that are used in this topic. Now, to do this, I need to do a fair bit of writing and drawing, so I'll change to PowerPoint mode. Here we go. I will be referring quite often to the ionisation of acetic acid in aqueous solution, represented by this equation, by way of example. I hope when you see this equation, or we talk about ionisation of acetic acid, you imagine the solution in which it's happening, and you're visualising the molecules and ions in that solution rather than looking at the equation. It's so important to distinguish between the reaction and the equation, and you'll see that this is extraordinarily important in understanding the jargon that we use. Firstly, a reversible reaction. In relation to this exemplar reaction, of which this is the equation, if all these species, acetic acid molecules, water, acetate ions and hydronium ions, are all in a reaction mixture, then both of the changes, this and this, represented by these equations, which in fact are that direction and that direction, happen simultaneously. One is the reverse of the other. Reversible reactions, in which these two reverse reactions are happening, are represented with the arrow, the double arrow symbol. That symbol doesn't mean that this reaction is at equilibrium. Maybe at equilibrium, maybe not. But it is capable of achieving an equilibrium condition. Now, direction of reaction. It's common to say that reactions of a reversible reaction go in reverse directions, opposite directions. But direction of a reaction? What's meant by direction of reactions? Chemical reactions don't have direction in the sense that there's any change of location. The only directionality is in the way the equations are written. So the arrow in a chemical equation like this one doesn't mean that these things move to there. They mean that these things change into these things. And there's no sense of change of location associated with that. So let's zoom into a tiny region of reaction mixture. I've got no possibility of representing to some scale. I'm trying to get some perceptual sensation. Tiny regions of mixture in which the reversible reactions are going on. And at any one instant, we've just captured a snapshot in a femtosecond, and there are collisions taking place. Let's say these collisions indicated in red are places where a hydrogen ion is being transferred from acetic acid molecule to a water molecule. The ones indicated in blue are the ones in which a hydrogen ion is being transferred from a hydronium ion to an acetate ion. So whatever happens here at this collision is the reverse of what happens there. And if there's the same number happening, this is in a condition of equilibrium. There's no physical movement, change of direction of these species, change of what the species are, but no directionality. So technically, we might say, in relation to either that direction of reaction or that one, the reaction is represented by the equation written. The reaction that happens here is represented by the equation written in that direction. Right? It's only the equation that has directionality. Now the terms reactants and products. If we burn methane in air, and the equation for that is this, the reaction essentially goes to completion. It goes until there's none of either methane or oxygen left behind, and this is formed in substantial amounts. In this case, there's no doubt. Methane and oxygen are the reactants. They're what react. And carbon dioxide and water vapour are the products. They're what are produced. But in the case of our exemplar reaction equation here, this reaction, a reaction mixture in which the reaction, represented this way, is happening, might be formed from any of a number of starting situations. We might have this reaction by adding acetic acid to water. We might have this reaction mixture by adding a solution of an acid to a solution of sodium acetate, or by mixing acetic acid and a sodium acetate solution and some acid with hydronium ions in it, or by mixing a solution of an acid and acetic acid. All these ways are possible. Now it's not so clear what the reactants are, what reacts, and what is produced. Really, all of the species are reactants. They all take part in the reaction. Nevertheless, it's common practice to use the term reactants for the species on the left-hand side of the equation and products for the species on the right-hand side. It's just important when these terms are used to recognise that they're used in a sort of loose sense. Now we have the term net reaction. If a reaction mixture is not at equilibrium, the reverse reactions in a reversible reaction will happen at different rates. One will go faster than the other in such a way they bring the mixture to equilibrium. If in a particular period of time more of reaction to the right happens than to the left, then there will have been a net increase of species that are written on the right side of the equation. And we say that there was net reaction to the right. It's the difference between how much is formed of those species on the right and those species formed on the left. In simple terms, if we put 100 marbles in a box and we take out 75, there's a net change of 25 marbles. Now, we say it as net reaction happens to the right. At least some people do. I try not to. We represent it by an equation with an arrow with directionality. But this is what it means and how we should visualize it. Looking deeply, zoomed in to a tiny bit of the reaction mixture. At one instant, we have collisions, red ones indicating formation of acetate ions on the right-hand side of the equation, and blue ones representing the reverse collisions which result in the reverse process. There are more of the red ones than the blue ones, and so there is a net reaction, increasing the amount of, or the concentration of acetate ions compared to the concentration of acetic acid molecules. Now, net rate of reaction, again, is a difference. It's the difference. So rate of reaction is the change of amount in a unit of time. And if these two reactions are happening at different rates, then the net rate of reaction is the difference between the rates of these two reverse reactions. Again, by analogy. Imagine an all-day concert. It's going to be open from 9 a.m. till 5 p.m. People can go whenever they like for as long as they like. Early in the morning, you'd expect a lot of people to be coming, not many going. 2,000 people per hour, that's a rate, are arriving. 300 people per hour are leaving. There's a net change of 1,700 people per hour. Late in the afternoon, not many people are coming, 450 people per hour. The rate of people going is 1,160 per hour. Then the net rate of change is the difference, 710 people per hour. In a reaction mixture at equilibrium, you'd expect the net rate of reaction is zero, because those two reverse reactions are producing species and removing species at the same rate. Now, we use the terms perturbing and disturbing, mean the same thing, systems at equilibrium. Imagine if we had a reaction mixture at equilibrium. We can change the conditions of that reaction mixture so that at least in one instant it's no longer at equilibrium. And we can do that by either changing the concentrations of one or more of the species or by changing the temperature. Then we say the condition of equilibrium has been perturbed or disturbed. It's no longer comfortably at equilibrium. And after perturbation, there'll be net reaction such that the reaction mixture comes again to a condition of equilibrium. And in doing that, we can say, and again I try not to, that in re-achieving equilibrium, the position of equilibrium shifts to the left or shifts to the right. Again, I emphasize that left and right have only to do with our representation in equations. Firstly, recognize that reactants and products are not in different compartments, and certainly not in two different vessels. They're all dispersed uniformly throughout the one reaction mixture. And I say this because there is some research evidence that many students visualize reactants in a vessel and products in a different vessel. And that's probably because we write the representation, the equation, with things in almost compartmentalized. But the terms left and right refer to the positions of the formulas in the equation and not to any position of species in the reaction mixture. This jargon, shifts to the left, shifts to the right, concerns a reaction which was at equilibrium and the equilibrium condition was perturbed. And then there is net reaction either to the left or to the right, as they say, such that the reaction mixture comes to equilibrium again. In our exemplar, if we're talking about equilibrium shifts to the right, that means that in re-achieving equilibrium, there's an increase of the species on the right concentrations or amounts and a reduction of the concentrations of the species on the left. My preferred way is to say that there's an increase in the ratio of this species to that species, because this concentration is going up and this concentration goes down as a result of this shift to the right. And a shift to the left means the opposite of that. And now, the slippery term, spontaneous. In everyday life, spontaneous means something that happens without prompting, rapidly, immediately. If you let go of a ball, it spontaneously falls to the ground. In the context of reversible reactions, chemical equilibrium, the word spontaneous has an entirely different meaning. It's got nothing to do with immediacy or rapidity, how fast it happens. In our context, the word spontaneous refers to a particular direction of net reaction. Which direction? It's that direction of net reaction that would take a reaction mixture toward equilibrium. That direction of net reaction is what we call the spontaneous direction, regardless of how fast or how slow, or if at all, it actually happens. Again, back to the ionisation of acetic acid. If we were to bump up the concentration of sodium acetate, at that instance, the reaction would no longer be at equilibrium, if it was before we added the sodium acetate. Reaction would happen, net reaction, such that the concentration of acetate ions would decrease and the concentration of acetic acid molecules would increase. Then would come eventually to equilibrium again. So we would say that some people would say this is net reaction to the left. That's the spontaneous direction of net reaction. That's the direction in which net reaction would need to happen so that the reaction mixture comes to equilibrium again. Okay. You might sometimes see reference to a spontaneous reaction. That really doesn't make sense. It's very loose language. Spontaneous applies to a particular direction of net reaction. Now, just to clarify that it doesn't have anything to do with immediacy or rate of reaction, imagine a vessel in which there is hydrogen and oxygen only. That mixture is not at equilibrium because the reaction represented by this equation has an enormous equilibrium constant and would only come to equilibrium if there was so much of that and essentially none of at least one of these. But we've only got hydrogen and oxygen and there's none of these. And that reaction at room temperature is infinitely slow. If we were to come back in 10 years' time, 100 years' time, 7,000 years' time, and it had always been kept at room temperature, no reaction would have happened. Nonetheless, this is the direction of net reaction that would take it towards equilibrium, and that's the spontaneous direction, so-called to the right, even though it's not happening. It's the direction that would take it, the direction of net reaction that would take it towards equilibrium. The infinite slowness has got nothing to do with its categorization as the spontaneous direction of net reaction. if we use anthropomorphic language, which I do, but many people say we shouldn't, I would say that the net reaction to form water is what this reaction mixture that we were talking about wants to do, regardless of whether it is able to or not. Okay, we can't have emotions of chemicals, but I can talk in terms of what it wants to do. By analogy, if we had water in a dam on the side of a hill, the spontaneous direction of flow is downhill, even if it can't do that. So, directionality is implied in the equation that we use to talk about reaction, but chemical reactions do not have directionality, change of location. So in understanding the jargon to do with reversible reactions and equilibrium, it's important to visualize into the reaction mixture rather than to look at the chemical equation.